So the next speaker is Patrick Cousot, and he will tell us whether Peter is correct or not.
Okay, thank you for inviting me. And today the question is Peter correct or incorrect? And I let you guess, each one has his answer. So, you know, Peter introduced incorrectness logic, so in that case he was incorrect. And is it really incorrectness logic? That's my question. And also he moderately enjoys other logics. For example, necessary precondition, to which I modestly contributed. He doesn't really like it because there are programs that don't satisfy any formula of the logic. So should he worry? We'll see. So then Peter says this must be formalized incorrectness, so I will try to contribute to that. So I have first an apartheid on the singularities of logic, which essentially is false and true is true. So you have things that like emptiness and universality. So emptiness means some programs satisfy no formula of the logic. And one example, if you have a logic for total correctness, if the program may not terminate, it satisfies no formula of the logic, and Peter like it. Necessary precondition is the same, but it doesn't. So then universality, some programs satisfy all formula of the logic, that is true, like if you take while true do skip, you take any OR formula, it will be satisfied, so, and no one cares. So this apartheid being finished, I go to reasoning on logics. So how do you design your logic? First, many people try and put this rule on, and then change the rule, and at the end they do some soundness proof, and then completeness doesn't work, so they remove the rule. I have a method. So first you define the natural semantics of the programming language in some structural, maybe fixed point form. Then you define the theory of the logic, which is a set of all true formula. And this is an abstraction of the semantics, or more precisely the collecting semantic, which is the strongest property of the program. And then you calculate the theory in fixed point form. You see, you have the semantic which is in fixed point form. You have an abstraction, so there are fixed point transfer theorem that give you the theory in fixed point form. And when you get it, you calculate the proof system. Calculate is very important, and there are two methods. One is fixed point induction, which that is how do I handle iteration or recursion, that's fixed point, and the other is called axial correspondence between fixed point and rules. So let's start with the design of or incorrectness logic. That was your aim, essentially. So let's start with the relational semantics. I have a very simple relational semantics for a language, which is essentially iteration. Then I have states, and then my semantic is angelic. I don't care about non-termination today. Then I have to have judgment for this semantics. So the first one says in state sigma, the execution of S may end in the state sigma prime. And the second says, in state sigma, after iterating a number of times, I come back to the beginning of the while in time sigma prime. So when I have this, you have this rule. You say the first A says, I am at the beginning, I iterate 0 time, I am still at the beginning. The next one say, I am at the beginning, the test is true, I do one iteration, then more iteration afterwards, so from the initial state I have n+1 iterations. And the last one say, if you have made iteration and the test is false, then you exit the loop. Simple. Then I have to express this in fixed point form. So I asked Mr. Axel, and he told me, this is the guy. You say you have a function, which is either the identity, you just arrive, or you make one iteration and you iterate more. You take the fixed point of this guy, you have what is possible at the entry of the loop, and then you exit when the test is false. So I will come back on Axel correspondence. Now let us abstract the theory, and there are two things, exact abstraction and non-exact abstraction. So the first abstraction is from hyperproperties to properties. I just take the union. Then you have an isomorphism, which is what is called post-image isomorphism. When you have a relation, you can take the right image of this relation, and that's essentially another encoding, which is exactly the same. Then the third one is the graph isomorphism. When you have a function, you can represent it by a graph, which is mapping which is the relation between initial and final condition. So you see, take our logic, you don't speak about hyperproperties, but program properties. Then this is the post, and then this gives you pre and post. So that's three abstraction, and there is another one because Peter wants to be not correct, so which is the negation, and which is a Galois connection between this power set in any order. So now we have to approximate the consequence, because logics have consequence rules. Some logic have consequence rule, not all. So you see I have here a pair is less than another pair if it is smaller component-wise. And then I can do two things. I take the post image of this guy, which is under approximate over approximate, and you recognize on the left something which is like the consequence rule of all logic. And I can also take the under approximation, and then you recognize here the consequence rule of incorrectness logic. So essentially, all logic and incorrectness are dual abstraction. I do the first I said, and I take one of these, and I have one or the other. Okay? But that's not enough. So I have to compare. I have to compare logics through their theories, because I start first by studying theories after giving the abstraction. So the first logic would be the strongest logic. That is, it gives you exactly the strongest invariant everywhere. You can do nothing with it in practice, but intellectually it's useful. Then you have OR logic, where you take the upper approximation of this guy, and then you have incorrectness logic, where you take the lower approximation of this guy. So you might be unhappy and say he claims that, but how will he prove it? I prove it by designing the theory, and I get what exists. And OR incorrectness logic is different. It is not the OR logic. You agree with me? You want to prove that OR logic is wrong, you take OR predicate and you put a not in front. That's what I am doing. And also I am using some post condition to try to have some consequence rule. And when you do this, you can vary the abstractions. And the one in red are the one that we study today, SL strongest, incorrectness logic, lower approximation, OR logic, upper approximation, and negation, which is not OR logic. Fixed point abstraction. We need that because to handle loops, if we don't have fixed point abstraction, we will have something like compute the strongest invariant, upper approximate you get OR, lower approximate you get Peter. We don't want that. So what we use is fixed point approximation, and the first one is that if you have the abstraction that commute the abstraction of the least fixed point if the abstract least fixed point, that classical 79, not yesterday. And so we get a fixed point definition of the theory of strongest post condition, the first logic that I defined, and it's kind of trivial, you see. It says, take the least fixed point, which is going to compute the strongest invariant, and negate to exit the loop, and this was, the P was a precondition I start with. Okay, so that's the formula that gives you the strongest invariant. Okay, so how do I prove that? You see, I have some computation, kind of trivial. Then I have something here which says there is commutation, so I can apply my theorem and I get the result, and it's equal everywhere. I've just got that by computation. So the formula I showed, I got it by computation. Then I have to design the full system, and first Mr. Axel come in, and it says, assume you have rules with precondition, postcondition on some universe. The premise is a finite subset, because proofs need, you take finite thing before, you have a conclusion and the axiom have an empty precondition. Then the deductive system is a set of rules, any set can be infinite. And then you define this deductive system, define a subset of the universe. And you have two ways to define it. The first is by proofs. That is, you have a succession of terms so that for any term in the sequence, you can apply a rule. The premise has already been proved before, and the conclusion is the next term that you are going to derive. And you look at all the proofs, you get all the things that are provable, and that's the meaning of the deductive system. And then you have another one, which is this one, which is the least fixed point of something which is called a consequence operator. And these consequence operators tell you, assume that X has some hypothesis, then I draw all possible conclusions from this hypothesis. So I take all rules that are included in the hypothesis, so the premise has been proved already, and I can take the conclusion. So if you iterate this guy, you will have first the axiom that depend on that thing, then the thing that depend on axiom, then axiom, axiom, axiom. You take the least fixed point of all these guys, and you get all the provable things. That's due to Mr. Axel. And so if you have, conversely, if you have a fixed point, there is always some deductive system, set of rules, for which the provable thing will be this fixed point. So we got the strongest invariant as a fixed point, and this gives us a way to rewrite it, which says, it's a stupidest way. Huh? It is, you take all possible premises. If it is a consequence by the operator, you add the rule. There are other ways to do it more intelligently, but at least this one works. And so we get a proof system which is sound and complete by construction. Okay, so let's go. But it is impractical because we have first, up to now, to prove the strongest condition and then apply the consequence rule. No one does that. So we need, another thing we need is fixed point induction. How do we handle fixed point? So look at these guys, you are in bad shape, but you have already done that all your life. The simplest one is Mr. Park induction, which says if you have a post-fixed point, you are above the least fixed point. Then you have Scott induction, which says if it's true for all the iterates and you pass to the limit, it is okay. But these guys, they are not the thing we want to prove. So it's more complicated. What we want to prove here is the abstraction of the least fixed point intersection some abstract specification is not empty. So you see, the idea is I want a counterexample. So I want something which derives from the semantics and is a counterexample. That's what it means here. So what I do, I take an atomic complete lattice here. Doesn't work. Then I have a function that preserves non-empty joints. That's the case of the fixed point we have seen. Then I have some Galois connection to get the theory. Then I have some predicate in the abstract which is not empty, otherwise it's not fun. It would be not satisfied here. I get an invariant so that it's a post-fixed point here. I need some well-founded set to show that I make progress. Okay, let's get it. And then I need a function that decreases, a variant function, so it is from the atoms of the invariant to this well-founded set, okay? And I need a sequence of atoms here, which may be infinite, so that the first iteration you pick an atom. Whenever you are in the iterates, you apply the function to an atom, and you pick, this will give you an element of the lattice, and you pick one atom, and then the last thing, it looks complicated, but you will see it's trivial at the end. So if the two consecutive axioms are different, then something decreases, and if they don't decrease, you have got the result. Okay, so, and it's sound and complete, or it's a bit more difficult, but easy. Okay, so let us now design the proof system now that we have this fixed point induction. And I start. The first thing, and I have a little theorem, here you see equalities everywhere, that says this consequence rule is useless. So you see, that's great. I have no consequence rule. Then I take the theory. So it is a set of initial precondition, post-condition, so that essentially you will have, so remember this is negation logic. So to have the true, I have to put the negation on the negation. Okay. So this says you start from the precondition. Whenever you make an iteration, you move to the next axiom. At the end, you exit the loop because it's negation. So you are, and then you have proved that your post-condition is wrong. That's a counterexample to our logic. And you see the computation, I start from the definition. I have induction principle that I use, and I simplify, equal everywhere, and I get the formula at the end. Nothing to invent. So now we have to do the rules, and that's kind of trivial because I use Axel method to get the rule which says with no hypothesis I want to do that. It's an axiom. In fact, the induction was in the fixed point. The rule itself is an axiom. Okay, so now let's think about incorrectness. What you have seen is the logic for this, not all logic formula. If you take Peter incorrectness logic, it implies. So it's an incorrectness logic in a sense. But it does not imply in the other way. So it's incomplete as an incorrectness logic. He doesn't like it. Huh? But in fact, Peter, you see, can do it because he will invent something which satisfies his formula, and then with the intersection will not be empty, which is what we prove. But Peter, you see, you can just reason on one state. And starting from P, you prove that you reach one state, and this state is not satisfying the post-condition, so this negates this. So was Peter correct or incorrect? Yeah, I think he is correct, because he is always correct, and anyway, no one wants to say the contrary. So, but it took the hardest way, because our incorrectness logic is the easiest and most popular way. Did you thought about that? No. It has proof verifiers and theorem provers that exist since years, because they are called debuggers. So what we have done here is we have proved that debugging is actually an instance or a proof for or incorrectness logic. And so essentially what we did, we made debugging a formal method. So at the end, happy 60s to Peter, who deserves it.
Yeah, we have time for one or two questions.
So he has a question, I am sure, if I can understand it. Huh?
I feel I would really like to have a long time in the pub with you to discuss these matters. But so you say I took the hard path, but I was majorly influenced by abstract interpretation. And,
Is that true?
Which you did. And so, but I have a slightly more technical question. So, over approximation, the O'Hare proof rule, just an invariant, is complete. That's not complete for the under approximation.
Yeah, but under approximation is the dual.
Yes, but it's not the dual theory because the simple proof rule is complete for over but not for under. And furthermore, finite unwindings are sound for under but not for over. So does this very general scheme, which is just very lovely, does this explain these differences? Does this explain the differences?
So you are wrong and right as usual. You are wrong when you say it's not comparable and so on. There are two things. One is the duality in the order when you consider the strongest predicates. And then they are completely dual.
The predicates are dual.
But to handle iteration, you don't want to have the strongest predicate. So that's where you introduce a fixed point abstraction. And then the fixed point abstraction are not dual. And so that's why the fixed point abstraction for or uses essentially Park induction over approximation of a post-fixed point, whereas you use essentially because it's Scott induction, that is you go from below and you remain below the fixed point. And these two guys are not, they are dual in the conclusion, but not in the method. So essentially for me, incorrectness logic is exactly the dual over logic, except for the fixed point induction, which arrive to dual conclusion by different ways. Are you happy with that?
I think that, we've both said almost the same thing, so that we agree. So therefore, if I'm incorrect, then you're incorrect. Or if I'm correct, then you... So would you agree to agree with me on that point?
I miss this one. My incorrect is the incorrect of all programmers. It doesn't work on an example. Your incorrect is much more complicated. I know many examples on which it doesn't work, and that's too complicated.
Mine was motivated by not the human doing the proof, but by the computer doing the proof. And therefore, that's why concentrating on under approximation. Sorry.
This one I was lost.
Okay, so let's, I think maybe just take a offline. So let's thank the speaker.
Thank you.